In this video I'm going to continue with some examples taken from section 7.2. And again, I think you'd find it much easier to follow if you're actually looking at the same problems in the book. So you may want to page over to page 395, and we're going to start with number 16 from there. The problem says, find the z-score such that the area under the standard normal curve to its left is 0.2. The built-in function that we use for this is the inverse norm function. It's number 3 on this menu here. And when you're using this function with the standard normal, as we are here, it only needs one argument, and that would be the area of the left tail. Now in this case, the problem says that the area of the left tail is 0.2. So to find the z-score, that's all we have to do is put that in, and you can see that the z-score that would bound that region is minus 0.841 and some change. Maybe a good idea for you to draw a picture of this so you can understand exactly what the inverse norm function does. Let's take a look at number 22. It says find the z-score such that the area under the standard normal curve to its right is 0.75. So they're asking again for a left tail, but they're doing so indirectly. And so we can do this most easily. Let's just recycle our key sequence here. And we'll just go in there and edit that. The inverse norm always looks to the left tail. So when they give you a right tail, you have to translate that to a corresponding left tail area. And so you can do that by just taking 1 minus 0.75. And you can let the calculator do that for you if you want. And so the z-score would be as follows, minus 0.67 and some change. Let's also do number 24. Number 24 says, find the z-scores that separate the middle 70% of the distribution from the area in the tails of the standard normal distribution. Now the region that they're describing is similar to what you see pictured in problem 13C, right there on page 395. And the middle 70% obviously would have an area of 0.7. And so you got to remember the inverse norm always looks to the left tail. So think about this for a second. If you have 70% between these two z-scores, and by the way, they do have to be symmetric about the origin or about the mean, because if they aren't, then you really can't do this using the inverse norm function. That's why the illustration you see there in 13C is so important, because you'll notice that the z values are opposites of each other, and so it will be here. But if you have the middle 70%, then how much area is left to split between the two tails? Well, it would be 1 minus 0.7, so in other words 0.3. And half of that area is going to be in the left tail, and half will be in the right tail. So you can easily figure out that the area of the left tail would be 0.15. If you want the calculator to do it for you, you can do it as follows. Let's just recycle our key sequence again. And it's a little bit more complicated, but the calculation would look like this. We need to take 1 minus 0.7 and then divide that by 2, because again we're looking at the left tail only when we use this function. And there's the value right there. You could just as well do it by hand. You could key in inverse norm. Let's go back here and edit this. .15. And then just delete all the rest of that. Same result. So it's up to you whether you want to have the calculator do the arithmetic for you or not. But anyway, the most important thing is you be able to picture that region and give the z-values. Now we have the left z-value there, but the right z-value is going to be the opposite of that. So the answer to this would be negative 1.0364 blah 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 and positive 1.0364 blah blah blah. A few more examples here. I'm looking at number 36. Now this is actually very similar to the problem that I did in the previous video, number 8. It's just being asked in a slightly different way. So to do number 36, we can't use the inverse norm. We have to use the inverse, or the normal CDF rather. It's number 2 here. And since we're going to the right of z is 0.92, the syntax would be as follows. we would really like you to be comfortable going back and forth between a problem that's given like number 8 and a problem that's given like number 36. I mean, it's really the same problem, just with different values. Likewise, problem number 38 is very similar to number 10. Same problem, different values. So to do that using the normal CDF, let's just recycle our key sequence here. And for number 38, we want to go in between z is 1.23 and z is 1.56. So I'll just go in and edit that key sequence there. (1.23) and 1.56. And so there's your result right there. For number 42, that's very similar to problem number 6. So same problem, different values. And if you saw the other video, same thing, normal CDF. And in this case, since it's to the left of negative 2.69, we would go with negative infinity, which the calculator understands as negative 1 times 10 to the 99. And then the upper limit would be negative 2.69. And there's your result. And then for the last example, I'm going to do number 44, which is on page 396. And I want you to understand it's basically the same as problem number 12. Same problem, different values. So in the case of number 44, we can just recycle our key sequence here. Well, actually, we have to use the complement here to do this, so I'll just get it from the menu. It's going to be 1 minus the normal CDF. And the limits would be minus 0.38 and positive 1.93. And so that is how you calculate probabilities associated with the standard normal using your calculator. In the next video, we'll show you how to use the calculator with any normal.